Aruba browsing that's the source of the problem. All right, wait till I get this on. I'll answer your question, okay? Give me a second to get this on. You guys can hear me? Good? Okay, beautiful. So we agree that everyone, there's nobody who benefits other than the entity that discovers all of your clicks. Nobody else benefits from turning off caching. All of you suffer from all of Emily's requests. The network is more heavily loaded. The internet. There's a lot of traffic on the internet because web pages are uncacheable. Even the server, which handed out the Aruba page, that server now has to deal with more requests, right? So all parties in the end-to-end chain are actually negatively impacted, but there's a beneficiary, which is the person who found Emily that website to look at, which was Google. Okay? So if you look carefully, the old saying, follow the money? Do it, and you will understand how the design of distributed systems today reflects not just what is technically possible, but what has been done in order to monetize those end-to-end flows. Okay? Any questions? You had a question.
Why can't it be a win-win situation for both?
Why can't it be a win-win?
Yeah. So Emily's laptop would just check if there's been no change, and the Google servers know that she's still looking for it, and they don't have to send all that data back.
No. The very act of her checking is already causing end-to-end latency.
Okay.
You want if she could cache the file and it were callback based, or even if it was hit reload explicitly, I already have the page. Why should I ask the server, give me the page again?
Or you just want to check if there's been no change?
On a web page, so either you have to implement a cache consistency mechanism, like one of the ones I described. So callback would mean when she has callback on those objects until it changes, she's never going to have to ask again. Right? That would be one way. Or the last technique for the web was pass the buck, ask the user to reload. If Emily feels I should check to see if any new specials have arrived, she could click reload. Okay. Otherwise, she's only looking to see, would I like that beach or would I like that beach? Okay, to do that, I don't need to reload the page, but I'm forced to make the RPC, the HTTP request.
Do they send the huge pictures every time?
No, they don't send the huge picture. That is the one concession they make. So bandwidth might be okay, but latency is still paid because your HTTP request for the page goes all the way to the server, which gives you back the page, and you get a hit only on the big images, not on the page itself. Yes?
How do you get your browser to ignore the uncacheable?
You could hack your browser. Firefox is open source. I don't know if Google Chrome is. I don't think Chrome is, right? But Firefox is.
They're older version Chrome is, I think.
Maybe. But the only way, none of the companies will do it for you. Microsoft makes money from advertising too. So Edge and Explorer are not going to do it. Google certainly won't make Chrome do it. Firefox, if it's open source, you have some hope. You can go hack it, turn off the uncacheable bit. You might have to remember to turn it back on if you're checking stock prices or something, or your bank balance. But your web browsing will just speed up, accelerate amazingly, because you won't be paying all the end-to-end round-trip latencies. Other questions? Yeah?
So is turning off cache only done by the browser, or does the server also
Well, the server doesn't know anything. It's all done by the browser.
It's a similar question. So if it's all done by the browser, is it possible that the browser keep track of the clicks but actually fetch it from the cache so that it can send the stuff back to the server so that Google knows?
Remember what the problem is. In a network in which latency is not trivial, just the act of even making a tiny 1-byte request already slows you down. So the only way to win is by total silence. Okay? So either callback-based caching or leases or pass the buck. Right? So if the user explicitly reloads, but other than that, if it's cached, it's assumed to be good. Those three will give you zero network traffic.
On Tuesday, we discussed the skip scary parts version of caching, which requires that the server knows that you're making
But that's because there was at least some genuine scariness in the workload. Emily dreaming about Aruba is not a scary workload. Right?
So is this kind of
Aruba says, well, the people in Aruba, Emily said, the people in Aruba might think differently. But seriously, I mean, there's nothing, from a workload point of view, this is single user, read-only. What's to worry about here?
So it's just it's the same principle, just applied in a different context. So, skip scary parts is because there's multiple writes, versus here it's just...
So there, the problem had to do with genuinely, I have multiple users in the distributed system, some of them actually making modifications. This is read-only access. Even if there are 1,000 Emilys in the world, all doing reads, their caches should still be good, right? There's no right. If people in real time were posting pictures from Aruba and this web page is constantly being updated, okay, so maybe there's some reason to debate whether one of those other approaches might make sense. But this is a situation where the workload is totally benign, perfect for caching, and deliberately it has been neutered. Yes?
Why can't all of the advertising quickly in bundles so that you don't have to send it on demand to the advertisers, and when it's when we have a cache miss and we find it necessary to communicate with the server, that's when we send all of our bundled data stored from previous clicks all at once. So that
The problem is that people are very good at avoiding advertising, right? When it starts coming on TV, you switch channels. So advertising is only useful if from your point of view, you're forced to watch it. I kid you not, it's true, right? What's the point in telling me about Aruba if I'm not looking at it? So this is like a cat and mouse game. Okay, but there's one group of people who figured out how to make this bug into a feature. Okay, and I'll tell you how they did it. All right, so we finished this. Now I'll tell you how this problem could have been solved in the late 1990s differently, the road not taken. The browser running on your client is totally aware of every reference you make. The browser could keep track that Emily clicked on this web page in this order, at this timestamp, right? It could keep the clicks. And maybe once every half hour, it could transmit to some site. Here's the information. The problem is, first, in order for the reporting to be honest, you have to trust the client. In the late 1990s, the dominant operating system on the planet was what? Windows. Are you kidding? It was MS-DOS. Okay, and Windows 95 and 98, the GUI part was Windows, but the underlying file system and trust were all basically MS-DOS level. And MS-DOS has not even the concept of separation between kernel, which is trusted, and application space, right? So you couldn't implement this even if you tried. In any case, there's no incentive really for a world in which this model works. So technically, this would be the optimal solution, that the closest cache records references and tells, okay, here's what was looked at. But of course, this is a violation of privacy to a certain extent, right? Because why should the world know how often I looked at this? So making the case that people will voluntarily share what they're doing, it's not a viable assumption. Marking the page as uncacheable forces you to share that knowledge. You have no choice. Okay? So, there's a group of people who figured out how to make yet more money while keeping Google and Facebook in business. The idea is your project 2. In project 2, the cache you're implementing is not integrated with the client. It is a separate box called a proxy. That proxy could be a third party. It could have a business relationship with Google and Facebook and others. And it could certainly eliminate a lot of the latency by putting the proxy close to the user. So if there was a proxy in Pittsburgh, then Emily's HTTP request would only go to the Pittsburgh proxy cache. They would not have to go to wherever the site was she was looking at. So the people who figured this out, this is called a Content Delivery Network, CDN. So if you hear this buzzword, the whole reason for needing this is because of neutering of caching at endpoints. Okay? The additional, whoops, where did that go? The additional feature that Akamai, so the company that figured this out was a company called Akamai, which is a big company today, very successful. And interestingly, their success motivated all these players. Google has CloudFront, right? Windows Azure CDN. Every big player has their own content delivery network. One of the really interesting aspects is what is called late binding of parasitic content. And this addresses the question that the gentleman at the back asked. This is how they address your question. Okay? So how do CDNs work? Let me walk you through an example. Let's say there's some content provider, something that people actually want to go look at, okay? Say, it's the New York Times. So New York Times, they produce content every day. In fact, even during the course of the day, some news stories, what's happening in Ukraine, what's happening in the Midwest with the weather. I mean, things change, news stories appear. So viewed as a server, there's a lot of locality because lots of people worldwide are looking at it. Sometimes they might look at an article again, possibly. But the important point is that most of the time those articles don't change. So the PDF or the HTML hasn't changed since the last time you looked at it. But they might change once every 12 hours or so because an old news report is updated to reflect current reality. So what New York Times does is it produces the skeleton of the web page. And in that skeleton, it leaves behind blank spaces with a notation for Akamai to say some advertisement will come here, okay? And some half-page advertisement will come here. And a small little quarter-page advertisement will come here, and so on. So these are blank. Because the folks who produce the paper, let's say they're in New York City. This paper is read worldwide. Advertising something that is New York specific is not very useful. You need to customize it locally, okay? So this is the Pittsburgh Akamai server. And one of these users is Emily. And some of the others are you. Your references to New York Times using DNN lookup redirection, right? DNS lookup redirection. First time you contact, you might go to New York Times, but you get redirected to Akamai. You don't even know. You think you're looking at New York Times, but it's actually coming from the Akamai server. The Akamai server takes the raw content from New York Times, and local Pittsburgh advertising brokers have figured out, Mad Max on, I don't know, somewhere in Oakland, and some other restaurant somewhere else, and something else for Valentine's Day, and so on, right? I mean, they're all very local. The blank spots on the page are filled in with these advertisements. And now the actual web page seen by the user is a combination of the raw content plus. So I call it the intrinsic content, what comes from New York Times. That's what you really want to read. And then there's parasitic content, which you're forced to read. Right? It tells you about Valentine's Day, even though you don't have a date. What do I need it for? Right? Or it tells you about Aruba, even though you're broke. Right? You aren't going to go on spring break, but hey, it's just to make your life more miserable by telling you where you could be if only you had money. Right? So, if you lived in somewhere else, Kansas City, the same thing happens. It's the same New York Times page. But the folks in Kansas City have sold advertising locally. And so the same page is now decorated with parasitic content that is locally customized. And the same is true locally. So look at the value chain here. New York Times makes money. Presumably you pay them a subscription. Akamai certainly makes money because what it does is it does caching for New York Times. It does the merging of the web pages with the advertising. And then there are brokers locally who benefit because they're able to sell advertising. So they've created value from a non-problem. Right? Because all Emily wanted to do was to look at the New York Times page. And she didn't want any of these intermediate things. Her browser was perfectly capable of caching the page. But you're forced to use this. Any questions? Yes?
For this, is like, New York Times have to sign a Akamai to like see the split up, or is there like, are there multiple CDNs in like one location that also?
Oh, a CDN consists of multiple servers like this worldwide. So the combination of New York Times and Akamai, typically it's Akamai, using your IP address and where your request came from, will tell you which one is the closest server in the content delivery network.
Is Akamai just like one company that does this?
Akamai is one company.
So like if there's like other companies too?
Yes, each of the Googles have their own CDNs. Facebook has its own CDN. Initially, they all used Akamai, but then they looked at the bill from Akamai and said, you know what? We could be doing this ourselves. So, but there's still enough content. So if you look at New York Times, Google is a tech company. There are people that can implement a CDN. The New York Times has writers and journalists that prefer not to have to implement a CDN of their own. So typically, it is the case that Akamai's business uses all of the content providers who are themselves not tech savvy and themselves not likely to implement their own CDN. But the same picture works regardless of whether this box says Akamai, or it says Google CloudFront, or Azure CDN from Microsoft. It's the same idea. Other questions? I saw a lot of hands. Yes? What is PC? Parasitic content is advertising. It's a parasite. Parasite is something that piggybacks on something else. It's something you really don't want, but you're forced to live with. Yes?
Are CDNs used in like video streaming services?
Yes, they're even more effective there, right? Because the size of those things is big. I will be covering that later in this lecture, so just hold that thought. Other questions? Yes?
Does New York Times pay Akamai or does Akamai pay New York Times? 'Cause
Oh, New York Times pays Akamai.
okay, wow. For the latency, that's the only thing they're getting, right?
No, they're getting back also various kinds of usage statistics. What kind of articles did Emily read?
They would have got that anyway
How would they know that?
if they were hosting their own server, which is the other alternative.
But now Akamai is telling all of these statistics to them. It caches everything. Emily never actually has to go back to the main server. All of the requests are handled right here. So it is giving them valuable information in a usable format without them having to collect it themselves. They will pay for that.
When Akamai does this also means that New York Times can run a much smaller server, right?
Yes. So
They don't need to do contact center.
correct. Now New York Times will probably be using an Amazon server, a cloud-based server, but the amount New York Times pays to Amazon is less because of what they pay to Akamai. And as far as the advertising revenue goes, there's nothing technical about it. It's purely business. Most likely, I'm guessing, there are three parties here. There's the New York Times, which is generating the intrinsic content. If the intrinsic content is junk, nobody will want to read it. There'll be no users. So they're generating value. The parasitic content, there's a broker who's actually finding all the local advertisers. So they're delivering value, so they get a share of the advertising revenue. And then there's Akamai. So there's some business deal worked out in a smoky back room that says, this fraction of the advertising revenue comes to me, this much of it goes to you. There's nothing technical about it. It's pure business. Okay. Now you know the deep dark secrets of the internet, okay? So if you had the Wall Street Journal or Fox News, the story is the same. Notice that it's the same Akamai server. So from Akamai's point of view, the investment they make in putting a server physically at Pittsburgh, maintaining it, etc., that cost is amortized over all the users who pay them money. Wall Street Journal, New York Times, CNN, Fox News, you name it. Okay? All right. So, what this content distribution network sort of brings out is an important point, which is the last point I'm going to make, and then we are done with caching. Caching, as I told you in the very first lecture, is an idea that can be applied at many levels. You can have a browser cache, which in fact you do. And if you get a hit there, that is the best. Nothing beats getting a hit in the closest cache to you. All right? Because if I get a hit here, I don't even have to contact. I don't even have to go over the Wi-Fi link to the L2 cache, which is Akamai in Pittsburgh. Akamai in Pittsburgh could have yet another bigger cache, maybe for all of the United States or for the eastern part of the United States, right? So this idea can be recursively applied. But the important point is it is always, this co-located cache is the most precious cache. To the extent you can get hits in it, you completely avoid all networking traffic. All right, and the takeaway message is, in addition to the original rule, technical excellence is only weakly correlated with business success, we now have a new rule. Rule 2 says, business success may hurt technical excellence. A lot of people make money. That CDN shows lots of people making money. You suffer. Okay, so with that, we come to the end of caching as a topic, and I am going to begin the next topic. It's a perfect topic because it's only about half a lecture long, and that's what we have. So you can think of prefetching as either a sibling or first cousin of caching. Caching exploits temporal locality. Prefetching exploits spatial locality. And the gentleman somewhere at the back there asked me about streaming video. Caching is not very useful for streaming video. From the viewpoint, you rarely watch the same movie twice. Maybe if you watched it last year, you might watch it again. But, that's a long gap. So classic caching is unlikely to help there. But Akamai caching your movie makes sense because there may be a lot of Pittsburghers who want to watch that movie. So that cache is shared by all of them. So from the viewpoint of having to fetch the bits from wherever, Los Angeles, server, Warner Brothers, or whoever has the ownership of those bits, caching them at Akamai in Pittsburgh wins in that sense. Further, by doing it ahead of time, when you watch, prefetching can be used to reduce the stalls, the spinning wheel, which says buffering. Prefetching is how you avoid that. Okay? So in temporal locality, you make the bet that the future is very much like the past. Now, that's the basis of temporal locality. You may be wrong, but it's a bet. Prefetching says something different. It says, look, I'm pretty confident that the future is not going to look like the past. But it's not random. It's predictable. Because it is predictable, I can act on it now with confidence that it's going to be useful. If I'm watching frame number 1 of the movie, the chances are very good that I'll watch frame number 100 because it's coming a few seconds later. Will I be watching frame 10 million? Probably, but I can't be sure. If the movie is bad, you might quit. So the horizon of predictive accuracy drops as you look far into the future. Into the near future, your predictions can be very accurate. It's a little bit like stock market price prediction. If Google is doing well today, chances are good it'll be doing well tomorrow. But will it be doing well next year? Next decade? Companies have been known to go out of business in less time. right? If the uncacheable bit got turned off by Murphy, right, profits would sink. So how do you come up with the concept of nearby or next? So there are many, many examples. The easiest to understand is memory. Prefetching with main memory is easy because you have addresses, and so numeric proximity is easy. On disk or flash, you can treat it like memory, but it's not so useful. The reason it's not so useful is because the proximity is logical proximity. So if my data structure is not an array, but if it's a linked list, element 1 may have been malloced, element 2000, which was malloced many minutes later, happens to be allocated right next to item 1. So at the numeric level, they're next to each other. But the pointer from element 1 to element 2 takes you somewhere at the end of the address range in memory. So it's basically, you have to look at the data at the correct level of abstraction to discover the notion of nearby. In the case of a linked list, numeric address has nothing to do with proximity. In the case of an array, it does. In the case of a hash table, there's no definition of proximity, because by definition, you are using randomization to destroy any possible inference of proximity, right? So frames in a video stream, I've already given it to you. Now notice, going back here, that if I looked at packets on the internet, I may see the packet for frame 1, and then I may see the packet for frame 31. And the packet corresponding to frame 2 is far, far away. It took the wrong route, because at the moment it was transmitted, the internet routing table said send it that way. And then by the time frame 30 came along, the routing tables had been updated to say go this way, and this way happens to be much faster right now. So notice that on the network, the ordering of packets may not be in order. It is only at the very end, if it's sent by TCP, it's TCP that is doing the reordering. If it's sent by UDP, then it's whatever transmission protocol is being used that is using it. The same idea applies at bytes within a file and files in a directory. If I have a big directory, the fact that they're all in the same directory is some notion of proximity. If I access foo.c, there's a very good chance I will access foo.h. And if my program happens to be the C compiler, there's a very good chance I will be accessing a.out. Right? So you see how that knowledge is actually available at a higher level. It's lost at a lower level. So the trick to prefetching is to view references at the correct level of abstraction. Okay? And I think I mentioned before, in a social network like Facebook, the friend relationship can be viewed as proximity. You can use it for prefetching. Okay? All right, so here's the big picture. You're going to advance, instead of waiting until the demand access, you're going to fetch the data in advance. Now, how far in advance do you fetch? If you fetch completely before, so far in advance, that all of the data is local before the demand for that arises, you get a cache hit. There's no delay whatsoever. It's fantastic. The problem is that guessing that far in advance is often difficult. If I have to guess only a little ahead, my success rate is likely to be higher, but then I may not be able to fully mask the delay, the end-to-end latency. It'll still be shorter. If I generated the demand request 100 milliseconds ago, if I generated the prefetch request 100 milliseconds before the demand, you can subtract that 100 milliseconds from the total service time. Okay, so anyway, this does win. So what's the catch? The catch is, if you're wrong, you pay a price. And the price can be quite severe. It can be things that actually hurt, not just don't help you win. First of all, you're generating extra network traffic. You're generating extra server load. You're using up your cache space for stuff that might be useful, but you're not sure. And if your cache was already full, you might have booted out something that is actually important. So from all angles, prefetching is a double-edged sword. If you have high confidence that this prefetch is a good one, go ahead. But if you're not sure, you should think twice before doing the prefetching. So this is why, in the case of caching, demand caching, there's no guessing. There's an application which is actually done and open. There's no doubt here. This is made, the reference has happened. It's being blocked. So the work being done is not prefetching, it's not speculative. It's actual work that needs to be done. So one of the big challenges is also that demand requests get delayed behind prefetching traffic. So let's look at a server, okay, and see how it works. So if this is my server, prefetch request 1, prefetch request from client 1 is here. Then there's another prefetch request from a same client. Then one from client 2. Then another prefetch from client 3. They're all waiting. They're queued up at the server. Then comes demand request 1 from client 1. Why didn't client 1 send the demand request first? Well, because execution was proceeding at a certain pace, and it hadn't yet reached that point in the program. These prefetching requests were generated in advance, optimistically. But they're hogging space in front of the request, which is really the more important one. Your program is blocked now, waiting for this demand request to be serviced, but I've just made its life miserable. If you had turned off prefetching, you would not have any of the P's, the queue length would be 0, the demand request would be serviced immediately. And to add insult to injury, if none of these prefetch requests actually turned to demand requests, like your guesses were wrong, you slowed down something that was really important by making a bet that turned out not to be a winning bet. So prefetching and getting it right is quite tricky. Any questions before I go on? Yes? Can I go over what?
Does the server
Yes. In fact, that is the solution. The solution is exactly what you are saying, which is if I had separate queues for demand requests and prefetch requests, and the server always addressed the demand request first, then this problem wouldn't occur. So good answer. How do you apply this idea to the internet? You can't. On the internet, there's no way to send this packet D ahead of these guys. I don't have control. Once I put the packet on the internet at this end, the transmission, the routing, the ordering is not under my control. Also notice that to implement this priority queuing mechanism, you had to modify the server. This doesn't work automatically. Now you could imagine implementing this as a proxy prefetching queue. You could do that, in which case your code would be the one doing the priority queuing. Okay. So when is prefetching most useful? So you know by now, we're now in month 2 of the course. You've had all of problem set 1. So you know that there are 2 completely orthogonal properties of a network: latency, or round trip time, right? And the other is bandwidth. The question is, out of the 4 possibilities here, when is prefetching valuable? So if I have a local area network, it means that my bandwidth is very good, it's high, and my latency is very low. Notice this pipe is broad and it's very short. In such a system, why do you need prefetching? Demand fetching works just fine. So life is already wonderful if you have a local area network. You don't need prefetching. Now let's consider the other extreme. I have a long pipe, and it's very narrow. It's a thin, tiny straw, a few bits per second, and the end-to-end latency is 10,000 milliseconds. It's awful. Now, prefetching allows me to mask the latency. It's fantastic, right? Because if I wait for the demand request, I have to pay the full latency. If I advance it in the timing, the request arrives at the server at the moment. It's as if you have shrunk and reduced the latency. It's so cool. Unfortunately, it doesn't help. The reason it doesn't help is because the bandwidth is so low that the fact that you are going to be accessing this big file doesn't help me send it any faster. If bandwidth is the limiting factor, advanced prefetch knowledge, you can't act upon that knowledge effectively. So this is a case where life is grim. There's nothing you can do to help improve matters. Your prefetching is not going to help you. Okay? That still leaves us 2 cases. I can have a situation where latency is low and bandwidth is low. This is a very weird kind of network. They actually exist. So for example, there's a wireless network called Zigbee, which has bandwidth of 250 kilobits per second. It's meant for small devices, temperature control, stuff like that. Okay, there's an emerging standard called LoRa for the Internet of Things, which has got a few megabits per second. Okay, and sorry, not megabits per second, kilobits per second. right? So it's even lower than ZigBee. But the latency is actually quite low. Okay? Here, once again, knowing that something is needed very quickly doesn't help you transmit the object. The bandwidth is needed if the object is big. Nothing else is going to help. So it turns out that the sweet spot for using prefetching is this last quadrant. Okay, the last quadrant is the case where my latency is very high. So if I have a space probe close to Saturn, at the speed of light, latency is 1.5 hours. Speed of light. That's a long time. But it is possible, it's not easy, but it is possible to imagine someday a high-performance network, maybe even gigabits. I don't think gigabits will ever be really possible, but there's nothing theoretical that stands in the way. If you could figure out how to generate enough energy, maybe with a nuclear power source, you might need an enormous antenna with huge gain. Maybe that's possible, right? You can wave your hands and imagine a gigabit link. You can do nothing about the latency, but the bandwidth is fantastic. In that case, you win big by prefetching, because the high bandwidth allows you to actually act upon the prefetch knowledge and make a difference. Okay? So this combination, the case of high latency and high bandwidth, if you are ever in a design setting where that combination exists, that's the point to ask, should I be using prefetching here? Because it's likely to win. I think I just covered all of this. Yeah, any questions on this? Yes? Hold on, I can't hear you. Knowledge alone is not enough, right? Suppose I get the request for fetching some big image. I receive it 1,000 milliseconds before the demand request. It's a long time. It's good advance notice. But this image is many megabytes in size, and I only have a 10 kilobits per second link.
Not enough.
It's just not enough. I can't act upon that knowledge usefully. That's the problem. In the case of this combination, I have enough bandwidth. It's just I need to know what to do. Knowledge and the resources to act upon the knowledge, both are needed. And that's what prefetching with adequate bandwidth gives you. So there's another way to think about this. Prefetching is a way to transform ample bandwidth into reduced latency. Yes?
If you had a really small bandwidth anyway, wouldn't you not be using that to try to transmit big files?
Yes, you could send those small number of bits ahead of time, but it's still going to take a long time for the rest of the bits to arrive. So as a practical matter, most applications cannot begin to do anything useful until the last bit actually arrives. So the only amount of time that you've really saved is the latency of the network. Whereas if I had a wide pipe and I got the notice, advance notice fast enough, I would have been able to transmit all of it and would be there by the time your demand request arose. So that is the difference, that if you have prefetching, what it gives you is knowledge, but to transform that knowledge into useful results requires you to have enough bandwidth. Yes?
Is there any kind of quantitative criteria in terms of the and the bandwidth?
I wish there were. Lots of people have tried. So far, I've not seen anything that I would characterize as widely applicable. In any given setting, you can mathematically model the setting, and the insights you get from that model will be useful in that setting. So it's well worth doing. I would encourage you to do this. But one that is universal is difficult. Yes? You have a question?
Oh, yeah. So is there a case that where we send prefetch request and demand request on the same object, and then if the demand request arrives back to the client slightly earlier, do we consider the latency wasted for the prefetch request?
I'm not sure I understand the question. Walk me through it slowly again. I have both a demand request and a prefetch request.
Yes, and the demand got back slightly earlier.
The demand request comes earlier.
Yes.
Well, then there's no problem, right? The demand request then is processed,
Yes.
and then the prefetch request that comes afterwards is a it's a frivolous request.
Yeah.
Right? So I say, so what I'm hearing from you is, suppose I have two threads at the client. One thread says, prefetch file A. But bad luck, Murphy sends that prefetch request by the slow internet route. By the time the application gets to the point where it says open file A, Murphy is sleeping. So that request gets to the server delivers the file is open. Eventually the prefetch request comes. The server is not clever enough to remember, so it sends the file again. Okay? And the client gets these bits and says, oh, the server is really in bad shape today. I didn't even ask for these bits and it's arrived. It'll just throw them away.
Okay.
Right? So, but your question actually addresses a point on the previous slide that I actually did not elaborate. I think, where is it? I think it's in this slide. Yes. The single most valuable tool to help with prefetching is cheap and easy abort. You know, if you're trying to send something to a printer and you actually accidentally sent the wrong file, instead of a 4-page problem set 2, you just sent the 4,000-page document. And the printer has started printing. If I can say, abort, I'm sorry, I know you've already started it, but stop, don't waste any more time, that would be okay. But if I don't, I'm stuck. I'm going to get the bill for the 4,000-page printout and a lot of other mad people because the printer will be empty, etc. On the server, to answer exactly the question that you asked, if the client were to send a cancel prefetch request and the cancel prefetch request arrived fast enough, then the server would know I can just ignore it. But of course, with the internet delivery semantics, you have no idea when your cancel prefetch request would come, right? So it's very difficult to know. In any case, on the internet itself, once a packet is transmitted, you have no control. So it's like the 4,000-page printout. If I can't, there's no way for me to cancel it. Those bits are going to transfer over the network. They're all going to arrive. You're going to take all of them and throw it into the trash can. You just clogged the network for no good reason, but that's the risk of prefetching. Okay. I believe we are very close to being done. Let me see. Okay. Here's an important point. In all of computer science, all of computer science, there are only two known methods to reducing latency. One is caching, where I pay the price once, but they then don't have to pay it again. The other method is prefetching, where I pay the price in advance so that I don't have to pay it at the moment when I need it. Caching and prefetching are both important because latency is the very difficult thing to improve. Bandwidth is much, much easier. Importantly, it takes expense, right? To make a 1 gigabit per second LAN rather than a 1 megabit per second network. It's a lot more work. It's a lot more expensive. The electronics are more expensive, but it's doable. Reducing latency is much, much, much harder. And not only that, what is worse is that we are using things like security mechanisms, encryptions, the use of firewalls, adding extra stages. Each hop adds extra latency. It doesn't affect bandwidth. Notice why it doesn't affect bandwidth, because it's the width of the pipe. It's not the length of the pipe. They can each provide enough bandwidth. You won't affect the end-to-end bandwidth, but you will affect end-to-end latency. So, given that modern systems use many more libraries, they use many more security mechanisms, nothing that I see tends to reduce latency. They all tend to increase it. So these techniques are going to be extremely important. And remember, even when caching is successful, the very first reference is called a cold miss. That price you cannot avoid, but prefetching can reduce even that cost. Right? So that's the other reason prefetching is valuable. It allows you to even reduce the cost of the cold miss, even the very first time. Okay, where do you get the knowledge for prefetching? One, you can look at previous executions. You can do machine learning on them. You can come up with inferences about what might be important. It is possible for the user to give you hints. Okay? There have been a few systems. Programmers can give you hints. One of the biggest problems is your program now becomes brittle because the comments, which are the hints, may not accurately reflect the changes to the code that you make. And so you change the actual code, but you don't change the hint. Well, the prefetching is happening according to what you said, but the actual execution doesn't reflect that. Right? So this is one of the reasons why these kind of approaches have had mixed success. Another approach, which has been tried and actually works quite well for languages, some languages, is for the compiler to do the prefetching. After all, it is analyzing the program. It is building up the knowledge. It's using that knowledge for checking, for type checking, all kinds of things, but it could also generate hints. People have done this and done it successfully. An approach that has worked recently in the last 5 years has been to look at historical references and then apply machine learning on it and extract from it possible prefetching requests. For those of you who are interested, there is a little bit of work I'll point you to in the next slide. If cache space is plentiful, then the impact of latency is only, the server delays and the queuing delays. If cache space is scarce, then you should really, really think carefully about doing prefetching, because you might eliminate from the cache important items that are actually needed for demand access. And we already talked about prefetch too late. This is the question that you asked. Okay. Prefetching is a special kind of forward-looking execution. The general theme is called speculation. It's too broad a topic for us to cover in this class, but I just want you to know this and know this name, because there's a lot of research today on what is called speculative execution. If I have 32 cores on my machine, and right now I'm using 4 cores, what are those other 28 cores doing? They're doing nothing. Why not put them to work? Perhaps they could do some processing now that could be useful in the near future. Right? So this idea, same idea, except prefetching applies to data. Speculative execution is generalized to mean any kind of computation. Right? So if you thought prefetching was hairy, speculative execution is even hairier. Right? So one example of the combination of these ideas is in your optional reading. It's called data staging, where what you're doing is prefetching not to your local cache, but a future cache that you'll be close to. So let's say I'm on the plane. I happen to have a very poor network connectivity, bad latency, miserable bandwidth. I get email. And I know from this email, I'm going to need this 1,000-page document and a whole bunch of big PowerPoint slides in the next few hours. Shortly after I get off the plane, I've got to work on this. The network bandwidth is so bad that there's no way I'm going to be able to prefetch anything. So this is an example where I have knowledge, but I don't have the bandwidth to act upon the knowledge. However, at the airport where I land, perhaps there's a proxy server. It doesn't take many bytes to make a prefetch request and say, don't prefetch it to my cache, prefetch it to that cache. So that when I get off the plane, I will have high bandwidth connectivity to that cache. I'm close to it. And that cache is warm. All the data I need has already been prefetched there. And so even though my machine will have demand misses there, they will be serviced extremely fast. So this is called data staging. It's prefetching to a different cache from yours, and that works pretty well. And, okay, I already covered this. All right, so as an optional reading, you can actually make this work for virtual machines. So think of a YouTube movie. A YouTube movie has the property, you're guaranteed, if you watch frame 1, it's virtually certain you'll watch frame 2, 3, 4, sequential access, right? It's very, very rare that you move the movie pointer and skip some parts and watch later. It's not common. Program execution, on the other hand, has that property. In the next class, we're going to learn about virtual machines. And interestingly, virtual machine execution can be combined with prefetching. If you want to know how, you can look at this paper. So we have 1 minute left. It's a good point to stop. I can answer any last questions. We are done with caching and prefetching. We're going to begin a brand new topic on Tuesday. See you all.